Okay, kids, let's talk a little bit about heat, temperature, and specific heat capacity. Not Pacific heat capacity, but Atlantic heat capacity. Pacific, Atlantic, specific. It's funny. All right, here we go. So first of all, let's talk a little bit about heat and temperature. Don't want to confuse those things. When you look at a thermometer, okay, it can tell you what the temperature is. If I was to run over to the thermometer, oh, wait a minute, I gotta adjust you. You need to be adjusted. There you go. I need to be adjusted too. I need a chiropractor. Ooh, okay. Hang on, right back. 70.5. Okay. Whew, I'm exhausted. Oh man, I just ran 16 miles and back. I can't do that anymore. When I was younger, I could. 70.5 degrees, the thermometer on the wall says. 70.5 degrees, and that's Fahrenheit. Better not be Celsius. Oh man, would it be hot in here and need an air conditioner? 70.5 degrees Fahrenheit. Now, if I were to ask you, what does temperature measure? A lot of times, people will say, well, temperature measures heat. All right. Oh, does it? No, Billy. Yeah. Temperature measures kinetic energy. Billy's not getting, he's getting upset. He's not happy. No, it doesn't. Well, think about that. Okay, let's say that temperature measures kinetic energy. To measure the average kinetic energy, and you'll see that actually. Some chemistry books will have that written in there. The temperature is the measure of the average amount of kinetic energy. What a bunch of crap that is. It's chemistry, okay? It's not physics. Physics is the apex predator, okay? We're up here. Chemistry's down here. At least it's above biology, which is way down here. Okay, now, anyways, point is, so temperature is not a measure of kinetic energy. Because if the temperature is 70.5 degrees Fahrenheit, and I ask you, okay, 70.5 degrees Fahrenheit, how much kinetic energy is that? 70.5? It doesn't make any sense. The only thing that doesn't make any sense about that is we all know that temperature is in degrees Celsius or degrees Fahrenheit or or Kelvin. You don't say degrees Kelvin, you say Kelvin. But heat, which is kinetic energy and heat, which are forms of energy, are measured in joules. The international system is joules. In America, okay? We sometimes still use calories to measure heat. Sometimes you'll hear the British thermal unit, another way to measure heat. But the international system is the joule. So if kinetic energy is energy and it's measured in joules, then how can 70.5 degrees Fahrenheit be a measure of kinetic energy since the units are completely different anyways? It can't. That's my point. Okay, so what does temperature tell us? It's an indicator. It's an indicator of kinetic energy. It doesn't measure it, but it does indicate something about it. In other words, it was 70.5 degrees in the room today, and let's say that I go outside and it's 50 degrees outside. Okay, well that tells me something about the kinetic energy. It tells me that the kinetic energy in the room, 70.5 degrees Fahrenheit, and outside the room, 50 degrees Fahrenheit, not the same. Kinetic energy is going to be higher when you have higher temperatures because the particles are moving faster. So it does tell me something about the kinetic energy, but it doesn't tell me a measurement of the kinetic energy, okay? So temperature is an indicator, not a measurement of kinetic energy. Okay, heat. Sometimes those two words get mixed up. What's heat? Heat is a form of energy. Heat is the way that energy, it's one way that energy can be transferred. Okay, there's two ways energy can be transferred. Okay, two ways energy can be transferred. One's by heat, and the other one is by work. Okay, work, and this is for another part. We're focusing on heat. So heat is an energy transfer mechanism. Heat always flows from hot to cold. We'll find out that that's actually one of the laws of thermodynamics. Thermodynamics. That's when thermos move, because that's what dynamics means. Thermal movement. All right, so heat and temperature, not the same thing. Heat is a measurement in joules. Okay, that one's in joules. Temperature is an indicator of kinetic energy. Now, we do use temperature, though. We will use temperature. We're going to show very shortly, to indicate how much heat's been transferred. Oh, you see? The temperature does measure heat. No, it doesn't. It doesn't measure heat, but we can use it to help us figure out how much temperature has been transferred. Okay, that's a different thing. Speaking of which, let's look at the equation for that. Called the heat equation. We're going to need this bad, Larry. Yes, we are. So the heat equation is Q is equal to M delta T Cp. That's the way I write it. I mean, sometimes if you have had chemistry before, you do talk about heat. You do talk about specific heat capacity. Let me turn you this way a little bit. There you go. Sometimes you'll see the equation as mc delta T. And sometimes students like to memorize that one as mcat. They see that as being a CAT, cat. Meow, meow. And they say, yeah, that's easy to remember. I just don't, it's not me, it's not me, it's not me, okay? Okay? It's not you, it's me, okay? Okay? Yeah, it's not you, it's me. Like, if anybody ever says that to you, if it's not you, it's me, it is you. Okay? Remember that. You heard it here. It's you. All right. Anyways, I don't like this one. So let's do this one. So this one says heat. I thought heat should be an H. It is. There are times when heat is an H if you're talking about enthalpy of a system and heat transfers. And so there are H's and there are Q's. They both mean heat, but this is the one that we're going to use here. Q does mean heat. Kind of weird, right? But it does. It means heat. M's mass, delta T, change in temperature. Cp, specific heat capacity. We're going to talk about that. What's that? So we can measure the amount of heat that gets transferred in or out of a system if we can measure temperature changes. But temperature doesn't directly tell us how much heat something is. But we can use it with two temperatures, a temperature difference, to come up with how much heat was transferred in or out of a system. Okay, so keep those separate, heat and temperature, not the same thing. Okay, temperature does not measure heat, okay, but we can use it to measure heat flow. Flow. Yeah, I saw her on a Progressive commercial. That's right, Billy. That's right, we did. Flow. Yeah, Progressive. I'm advertising for them. They should give me money. Okay. All right, now, we do need to know a little bit about this. Specific heat capacity. What is that? Let me write that down. Specific heat capacity. I mean, if you wanted a textbook definition of it, it's the amount of heat energy that it takes to raise 1 gram of something 1 degree Celsius. And actually 1 degree Celsius would be the same thing as 1 degree Kelvin, or 1 Kelvin, because the temperatures on Celsius and Kelvin, each degree, identical. They just start at different places. So the Celsius has negative numbers in it. Kelvin does not. Kelvin was developed because Kelvin said, hey, that's a great job you did, Celsius. And, but the thing is, though, we need to have no negative numbers if we're going to use temperatures and gas laws. So gas laws don't work with negative numbers. So Kelvin just kind of adjusted the Celsius scale and got rid of the negatives. But 1 degree on each one of them, identical. Now, so what did you just say about this? Say it again. Say it again. I don't want to hit the rewind. Okay? I'm moving along here. I got stuff to do. I'm busy. I know, Billy. Calm down. It's the amount of heat it takes to raise 1 gram of a substance. 1 gram is not very much. By 1 degree, and that's not very much either. So specific capacities are small amounts of heat, usually, a small amount of heat, to raise the temperature of something by a degree, or lower it. So if you want to lower the temperature, you're going to have to remove a certain amount of heat in order to get that job done for that 1 degree and that 1 gram. Now, let me just put down quickly just to make a comparison with specific heat capacities. Let's look at some of the numbers. Now, there's chemistry heat, specific heat, and physics specific heat. I mean, they're the same thing, but chemistry tends to use grams per degree Celsius. And then physics, the apex predator, that's my dorsal fin, by the way, and that was Jaws. As we all know, Jaws, awesome movie. You haven't seen it, go stop this video right now and go watch Jaws. Right now, we'll wait. Okay, it was good, right? Told ya. Gonna need a bigger boat. Right. Yeah, so anyways, where was I? Oh, yeah, some of these for different substances. Just some common things like water. So in chemistry, though, when we're talking about these values, we like to use a kilogram. So we use kilograms instead of grams, because in physics, everything is supposed to be in meters, kilograms, and seconds. All right, to make life easy for us in physics, we use kilograms. So water is 4,190, and that's joules per kilogram degrees Celsius. Now, in chemistry, you would have learned that as 4.19 or 4.186. I rounded to 4.19, so it might sound familiar if you've taken chemistry and you had to use that heat unit. But yeah, we use kilograms, so it's a bigger number. Okay, some other ones that are, you maybe just kind of comparing them. You've got copper. Let's get aluminum in there. Put aluminum in there. Aluminium, as they say in good old jolly good England, aluminium. Okay, sounds so sophisticated, those English. Now, this is going to be 900, 899 to be exact, by around to 900. Close enough for government work, that's what I always say. And you've got copper, which is 385. Then there's lead. I can't remember lead exactly off the top of my head, but it's around 160, I believe. You can check that, look it up. Okay, look it up. But it's around that. My point, and iron or steel is in the 400s. Zinc is in the 400s, something. So you've got these metals, which compared to water, have a much lower specific heat capacity. Yes, they do, much lower. In fact, you look at copper, for example, and copper is over 10 times, only like less than 1/10. If you divide that in there, it probably goes in there like 11 times or something, like 1/11 the specific heat capacity of water. So what does that mean? That means water, which is very high specific heat, can absorb a lot of heat before its temperature goes up. You have to pump in 4190 joules to get a kilogram of water to increase temperature. With lead, you only have to put in 160 joules to get 1 kilogram of lead to increase in temperature. That means that metals will heat up very quickly. That's what it means. So metals heat up fast, water heats up slow. Yes, it does. You know that if you ever gone swimming in Maine, Maine, off the beaches of Maine, that water is like, yeah, it's that cold. So you know that if you've ever gone in Maine. And the best time to go swimming in the ocean, especially Maine, is late August, early September. But it's hotter in July. That's correct, Billy. But the thing is, that's not when the water temperature is going to be the warmest. Why is that? Exactly, Billy. Why is that? Because it takes a long time for water to warm up. It has a high specific heat, so you have to pump in a lot of energy from the good old sun in order to get its temperature to go up to it's not so brr anymore. And that takes like mid to late August for that to happen. A long time because it heats up slowly. Metals heat up very quickly, very quickly. When I was in the Boy Scouts, it was my job to, one morning, it was a sunny morning, winter, we were out in the winter. I was camping in upstate New York in January. Boy, talk about cold. And I was making scrambled eggs it was my turn to make a meal. And I had this long kind of aluminum spoon. No, it was not a ladle, but a spoon. And I always had heard, I was probably like 11 at this time, maybe 12. And I said, yeah, metals heat up really fast. Let's find out. And not only that, I was bored, so there was nothing else to do. I know computers or cell phones, so what else were you going to do? Okay, so I entertained myself. And I'm funny, okay, funny. Okay. And so I took the metal spoon and I stuck it in the roaring fire. And I want to hold on as long as I could. See how long I'm going to hold on. I'm going to hold on. I'm going to do it. And it didn't take very long. Trust me. Don't do that at home, okay, for professionals only. I've been trained with this stuff. Yeah, I didn't hold on to it very long, and it was like, snow. Psh, okay? Yeah, don't try that at home. Dangerous. Heat up very fast. Heat up very slow. You know that water is a good heat absorber. You don't know, but you do know, because you know that water is used in the automobile. Where? Where in the automobiles it used? You put it in the gas tank, right? Don't do that, Billy. Actually, my brother did that. He was like 4. We were playing gas station at my grandfather's house. Yeah, he took the garden hose. He was the gas guy, so water, turned it on. Yeah. Oh, Grandpa he was not happy, okay? But I thought it was funny, He got in trouble. When your older brother gets in trouble, always funny. So anyways, where was I? Oh yeah, the water is used in the automobile in the cooling system. You know that. It's in the radiator. I thought it was just antifreeze in the radiator. No. Water's in the radiator with antifreeze mixed in. Now, actually, if you lived in Miami, Florida, you can get away with just water in your radiator because you don't have to worry about it freezing. Up here in New England, not a good idea. Okay, you don't want that. You need some antifreeze so the water doesn't freeze. But it's water that is your primary coolant. It is the thing that is like super awesome at keeping things cool. All right, okay, all right. You know that. You go swimming and you know you're going to cool water and you cool off, okay? All right, that's enough of that. Okay, so that's specific capacity. The higher the number, the more energy it takes to warm something up. If you want to cool something off, the more energy it's going to have to pull out of it to cool something off. Water is a great heat absorber. Okay, let's see. We want to do some calculations using this equation. And I'll do a very, very quick one here. We got 15 minutes of video going so far. I gotta move it. Let's do one quick calculation, very easy one. Let's say that you have a 100 gram, now remember I said 100 grams, so let's do physics. Physics likes kilograms. You can use grams as long as your CP value is in grams, that's okay. But let's do kilograms. So 100 grams would be 0.1 kilograms. And let's say I raise that 100 grams of, let's say it's aluminum. Maybe it's a piece of aluminum, 100 grams of aluminum. And I'm going to increase its temperature from room temperature, maybe it's sitting around at 20 degrees Celsius, and I want to get it to 40 degrees Celsius. Because who doesn't want to get their aluminum to 40 degrees Celsius, okay? Everybody does, everybody. Cool kids do. So you go from 20 to 40, all right? There's your change in temperature, 20 to 40. And we look up aluminum, and it's 900 joules per kilogram. That's why I switched to kilograms. You're using the 900 value, not the 0.9. 0.9 would be grams. And if I do the math on this, I will know how much heat energy that I get. So this is 0.1, and this is degrees Celsius, and this is kilograms. This is degrees Celsius, and this is in joules per degree Celsius kilograms. So those kilograms to degrees Celsius cancel, leaving me with joules. So if I do the math, that's 0.1 times 20. 20 times 0.1 is 2. And 2 times 900. 2 times 900. Anybody a calculator? Billy, get a calculator out. Come on. 2 times 900. What is it? I'll wait. I got 1,800. 1,800? Billy got 1,800. I'm trusting him. Okay. So that's 1,800. 1,800 what? Joules. One more thing. And that would be the amount of heat that you would have to put into, because heat can be taken out. But if you want it to go from 20 to 40, you're raising the temperature. So you're going to put heat into the system. Right? 1,800 joules. We'll do the job. Is a joule a big unit? Okay, a joule and a calorie. We use calories. We're familiar with calories in this country. Let's talk about that just for a second here. Calories. So it's 1 calorie is equal to 4.19 joules. So what does that mean? That means it takes more than 4 joules to equal a calorie. But wait, there's more. When we talk about this calorie here, we're talking about the small calorie. That's not the food calorie. The food calorie is 1,000 of those. So 1,000 of the small calories equals 1 big calorie, sometimes called a kcal, and that's a food calorie. All right, okay, wait a minute. Okay, let's think about that for a second. Let's think about that. So you're telling me that it takes 1,000 of these small calories equal 1 food calorie, and 1 food calorie is not going to get me through my day. Okay, maybe 10 will. I need 10 calories per day, and I'd be fine. Restro. A lifesaver. Okay, I like some wintergreen cherry, like cherry flavor. Okay, whatever. Lifesavers, 10 calories per lifesaver. So you would need 10 lifesavers. Okay, so 1 lifesaver is equal to 10 of these food calories. So that means this little calorie, we call it the science calorie, is really small. Because 1,000 of those equal 1 food calorie, and it would take 10 of those equal a lifesaver, which we all know is not going to be a very good daily meal. You're going to be a little hungry, aren't you? So what does that mean? That means the joule is even smaller than this, and that's smaller than that. So that means the joule is a very small unit of energy. A joule is small. It's not very much. Typically, when we talk about joules, we talk about joules in and out of the system. We end up adding or subtracting kilojoules because we need like thousands of them to make any significant difference in temperatures or heat or flow or whatever energy at all. So the joule is a small unit. Okay. That's it. Let's wrap up this video. We'll see you very soon. I'm going to go drink some coffee and get more energy because right now I'm exhausted. I don't have any energy at all. I bet you can tell that too. Okay, kids, we'll see you later.